Hello everyone, welcome back. Today we are continuing with Chapter 2, Part 2. And just to give you a quick recap, I'm going to go back to the notes that we had from Part 1, where we had defined a number of the different terms that we're going to be using, not only in this chapter, but through the rest of the semester. And we want to today focus on the derivative statements that we came up with. Each one of these statements down here is an instantaneous ratio of two terms. In the case of velocity, we have the instantaneous rate of change for position over time. For acceleration, we have the instantaneous rate of change for velocity over time. But then we can actually combine the two given the definition of velocity, and we can import that into the second equation. And so acceleration can also be described as the second derivative of position with respect to time. And what we want to do is we want to first of all discuss where this calculus stuff came from, how it's used, why it works the way it does, and then we will apply it to these three expressions to see what other kinds of equations we can make to help us in describing the motion of different objects. So now I'm going to switch over to a fresh page here, and we will begin our discussion on Chapter 2. And since our discussion will be pretty heavy on the calculus, we should discuss where the calculus came from. And depending on the class that you're in, any physics class that you're in is going to say that the mathematics that we know of was produced by Sir Isaac Newton back in the late 17th century, or mid to late 17th century. Or if you're in a math class, one of your math professors might say that the calculus was produced by another gentleman, a German mathematician by the name of Leibniz, or Leibniz, depending on how you want to pronounce the name. But this is, of course, a physics class, so we're going to go with Newton. And there's kind of a story behind the process in which Newton came up with calculus. He was a very inquisitive child, very interested in the way the world worked, and just could not settle for anything but a definitive answer as to why things were happening the way they were. So when he got old enough, he packed up and went to college and enrolled in all the courses that a typical college student of the day would enroll in. And he actually started off as a philosophy major because he found out that those philosophers would ask all the big questions, and they would get all kinds of answers. But what he didn't know was that a lot of those answers could not be proven definitively one way or another. It turns out that philosophy was the first step in the logic process of argumentation and trying to figure something out. But for Newton, he actually needed a little something more, which was mathematics, to describe what was happening with the world around him. And so he decided that he was going to switch his major over to mathematics, and then right about the time he did that, the Black Plague was making its third round through Europe, and so they had to shut down the university and sent everybody home for 2 years until the plague had run its course, and then the students were allowed to come back and continue their education. Well, Newton wasn't going to waste all of that time, so he decided to put his time to good use in trying to figure out some of the mathematics behind some of the more basic phenomenon that other mathematicians had not yet been able to adequately describe. And that phenomenon was gravity. Now there are plenty of stories behind Newton and gravity. A lot of those stories are incorrect. Some people will say Newton discovered gravity. That's not correct. The ancients knew what gravity was. They just didn't know how to describe it using the math until Newton came along. And Newton did that by inventing this new kind of math that we now call calculus. And so you can kind of imagine, after 2 years being in isolation, Newton comes back to school and says, "Hey everybody, I've got this new math." And if you had a classmate do that today, if they came back after being gone for 2 years and said, "Hey, I came up with this new kind of math," you might not take them seriously right off the bat. But what we're going to do right now is we're actually going to look at the process that Newton used to figure out the mathematics behind gravity. And what we're going to do is we'll take something like a ball and we'll allow it to drop. So we'll start with some initial velocity of 0. The ball is at rest just before we release it. And then gravity is going to take hold and it's going to start accelerating the ball towards the ground. Now, one thing that we do know about gravity is that it is a form of acceleration. And so that acceleration will cause a change in the velocity of the ball with respect to time. So the longer the ball falls, the faster it is going to travel. And because the velocity is changing, well, velocity is defined as a change in position with respect to time. If we do in fact have a velocity associated with this, then that means that the displacement of the ball is going to change with respect to time. Now here I'm using delta x to describe the displacement, and in our previous video we had used the horizontal number line as our x-axis, but now we have a ball that is falling in the vertical direction. We could continue using delta x if we wanted to, but it might be better if we used the more traditional labeling of delta y. And so as the ball moves, or as the ball displaces, it will, oops, sorry, I didn't mean to put the deltas there. I need to put the delta here. So as the ball falls, it is displacing and changing its position along the y-axis. So if we prefer, we could just as easily rewrite this as delta y over delta t. Alright, well, as the ball falls, it accelerates. As it accelerates, it changes its velocity. As it changes its velocity, it changes the rate at which it displaces. So if we were to take all of this information and cram it into a single idea or a graph, I'm going to take the change in position with respect to time, and granted the ball is technically falling in the negative direction, but I'm going to use the magnitude of the position. So what we're going to see is the ball will start at some predetermined position of 0, but as time goes by, the position of that ball will increase with respect to what looks very much like a quadratic curve. So this is not a linear expression. And we need to keep in mind what kind of mathematics were available at the time to individuals like Newton. Keep in mind there was no calculus because he hadn't invented it yet. So what comes before calculus? Well, you've got some algebra, you've got some trig, and maybe some geometry, and that's really it. All that stuff, that's pretty much considered prerequisites for entering a class like this now. So you know, take that with a grain of salt. You are more prepared today walking into an introductory physics course than anyone back in Newton's time. And so what we're going to do is we're going to investigate this graph and see exactly what's happening. And as I said, some of the best math that they had at the time were things like algebra. So let's go after this graph using some algebra. I want to pick 2 points on this graph, and I'm just going to pick 2 random points. We'll say that point and this point right here. So 2 points on the graph, and those 2 points will have corresponding values on the horizontal and vertical axes. So right here I have a corresponding position value, and I'm going to call this the initial position, because as far as the time is concerned, this measurement is going to come first, and this measurement will come later. So we'll go ahead and call that T final, and correspondingly this will be position final. Alright, well, let's hit this with some algebra. As I said, I want to figure out what is the slope of the line that intersects between those 2 points. And in algebra, slope could be found as the rise over run. So rise was the change in the vertical axes, run was the change in the horizontal axes. But the change in the vertical axes, if I take the difference in those 2 values, that's final minus initial. That's technically a delta. So I have delta y for the rise. The change in the horizontal axes, that's the change in the times. That's also a delta, delta t. And now I have change in position over time. Well, that's velocity. But when it comes to drawing the slope of the line that passes through these 2 points, so I'm going to go ahead and draw a line as best I can to go through those 2 points. I wanted that to be a different color. Try that again. So there's the line that goes through those 2 points. And how well does that line match up to the actual plot that we're seeing? And the answer is not very well. The slope only intersects at those 2 points, and at any other point along the original graph, we end up deviating some amount. And so this slope equation is not very good at describing the true velocity of this falling object. But if you'll remember from our previous video, we said that anytime we have a large time interval, the best that we can do is an average. And I said in the last video that any time interval greater than 0 is going to be too big. And so what we have here is actually the average velocity of this falling object as measured between the 2 time values, t0 and t final. If I were to choose some other spots on this graph, maybe I choose this spot and this spot, would I get the same average velocity? And the answer is no. I actually get a very different line with a different slope. And that's going to be true as we go all the way along the curve of this graph. I can pick multiple points along the way, but what I'm going to see is that the graph of the slope is continuously increasing as the change in position increases. But I want to be able to figure out, can I get a measure of the instantaneous velocity at some point on this graph? And the answer would be yes, we can do that if we can get our time interval to shrink down to an instant. And therein lies the problem. If I insert a 0 for delta t, then I'm dividing by 0, and that's no good. The math is going to blow up. So I need to figure out a way of basically tricking the math in allowing me to divide by 0 without losing all of the other information. So here's how we're going to do that. And I'm going to redraw our graph with our 2 test points. Go back to the blue. So here's our first test point, here's our second test point. So Newton took a look at this and said, well, this isn't going to work as is, because every time I try to plug in a 0 for delta t, all the math blows up. So Newton started his approach by relabeling and redefining a lot of the stuff that we have in this current graph. The first thing that he did was he picked up on the idea that this change in position was dependent on how much time has elapsed. So the more time goes by, the more the position changes. And so that meant that the position was actually a function of time. And position, as it turns out, is not the only function out there that can vary with respect to time. In fact, we don't even have to limit ourselves to time as the dependent variable. We can have expressions that change with respect to any variable. and still describe it as a function. And so that was the first thing that Newton did. He took the position function and said, well, let's just generalize it and call it a function f. And that way we don't have to limit ourselves to just a change in position. We can use this approach for any time-dependent function. Well, now that I have a time-dependent function on the vertical axes, I need to go back and redefine what those initial and final position values were. Well, the initial position, that's going to be our function evaluated at the initial time. In fact, we can do better than that. Let's do initial time. That's better. And then the final position, well, that would be the function evaluated at the final time. Alright, so back to the slope equation. Slope is rise over run. So the rise is the difference in the vertical, and the run is the difference in the horizontal. But I still have that delta t expression in the denominator. So I really haven't changed anything except that I've generalized the numerator so that I can use any time-dependent function. So now Newton said, well, let's take that time interval and let's shrink it down. We need to figure out a way to shrink it down to something that is infinitesimally small. And right now, the difference in these time values is just too big. So what we need to do is we need to generalize these time values as well. And looking at this, we might think, well, how much more can we generalize this? We have two unknown time values and an unknown time interval, delta t. Well, the way we're going to do that, the way we're going to generalize this, is since we don't know what either the initial or the final time are, why don't we just take that initial time and we can just call it generic t. And if that's the case, then t final would have to equal that generic initial time of t plus whatever time interval elapses. So we can take delta t final and we can replace it with t plus delta t. Delta t. And so we have t final, we have t initial, which is just t, and if we take the difference in those, we still get delta t. But now that we've changed the notation of the time values, we need to carry that over to the function terms, because those functions need to be evaluated at those specific time values. So our initial position, which was evaluated at t initial, is now just going to be evaluated at t. Our final position, which was evaluated at t final, will now have to be evaluated at t plus delta t. So everything that I've written down here for the slope equation needs to be updated. We have function evaluated at the final time minus function evaluated at the initial time. all divided by the difference in the time values, which is delta t. And this is Newton's default starting point for finding the derivative of a function. Now, looking at that, we still have delta t down in the denominator. The next step for us in finding the derivative of this function, f of t, is we need to take the limit of this slope expression as delta t approaches 0. But if we do that right now, everything's just going to blow up in our face. What we need to actually carry out this derivative process is a function. Right now, everything that I have in that expression in terms of f of t, well, f is just the generic notation for a function. I need an actual function that I can play around with. And so I'm going to just make up a time-dependent function. We'll say 3t squared plus 4t. So there's our time-dependent function. And I want to know what is the derivative of that function. And the derivative is really just a fancy way of saying what's the slope. Well, just by looking at that, all of you can probably do that in your head in terms of figuring out what the derivative is. And we do that just by using the polynomial method for derivatives. So we take the power, bring it down to the front as a coefficient, and then reduce the power by 1. So we're going to end up with a 6t plus 4. That is our derivative. So that's our goal. This is what we want to reproduce using Newton's method. So here we go. Newton's method says we need to take our function evaluated at t plus delta t, and then subtract the function evaluated at t, and divide all that by delta t. So here we go. Our function evaluated at t plus delta t. How do we do that? Well, we're going to take everything that was inside the parentheses for t, and we're going to replace it with t plus delta t. So f of t plus delta t will equal, and we had 3t squared plus 4t. That is now going to be replaced by t plus delta t. Now we do have a little bit of work ahead of us here. The t plus delta t in the first term has been squared, so we need to carry out the multiplication in there the proper way. Make sure that you're using your FOIL method. And when we FOIL that binomial, we get t squared plus 2t delta t plus delta t squared, plus the second term, well, that's just 4 times t plus delta t. All right, so that's the first part. And all of that, we have to subtract the function evaluated at t. Well, the function evaluated at t was just the function. 3t plus 4t, or excuse me, 3t squared plus 4t. So we have to take all of this and subtract that from it. So we have in the top a 3t squared minus a 3t squared in the denominator, so all of this is gone. And then I'm missing a, oops, I'm sorry, I have too many t values over there. There we go. And in the top I have a 4t minus a 4t in the bottom, so we're going to lose all of that. And let's just take a look at what remains. You'll notice I did not cancel out the 3's and the 4's because those actually have to carry through the parenthesis sets. But everything in the top of our expression is, let's see, we have 3 times 2t delta t, so that's 6t delta t, plus 3 delta t squared plus 4 delta t. So just double check, look through there for all the different terms. None of those are like terms, so I cannot combine them as of yet. But now comes the denominator, delta t. So everything that we have, I'm going to go ahead and write that down again. F of t plus delta t minus f of t all over delta t. We need to take the limit as delta t goes to 0. So what we now have is the limit as delta t goes to 0 of 6t delta t plus 3 delta t squared plus 4 delta t all over delta t. And we still can't take the limit without having the math blow up in our face. But now we can see the silver lining to all of this is that every term in the numerator has a delta t, which we can factor out with the delta t in the denominator. And so what we are left with in the numerator is 6t plus 3 delta t plus 4. And now we finally arrive at the point where we can actually evaluate our limit. We can now plug in 0 for delta t, and when we do that, the middle term is going to drop out, leaving us with exactly what we knew we should get 10 minutes ago, which is right there. Well, do we have to go through and use Newton's method every time we take a derivative? No. It takes a lot of time. There are a lot of steps. The more steps that are involved, the more likely we are to make a mistake somewhere along the way. But please feel free. Take the polynomial method for derivatives, where we have I probably shouldn't write it that way, but if we want to take the derivative of a specific term, maybe we have x to the n. That would be better. The method for that is to bring n down to the front, subtract 1 from the power, and then you have your derivative statement. So feel free to continue using that. The reason that this works is because after hundreds of years of people using Newton's method, eventually it came to the point where people started picking up on patterns as to what was going to happen with this process. And someone finally said, this keeps happening with every term inside the polynomial. Maybe we can use that as a shortcut. And that's what we use today. So feel free to continue using that. But now we can see that Newton's method is actually working. Newton's method is, in fact, providing us with an instantaneous description of the slope for any function. And so if we take that back to our diagrams here, when it comes to the change in position for an object, well, as long as we have a function that is describing how that object is falling, we can now apply the calculus to it and let the calculus tell us how things are going to be changing. Now, the one thing that is going to make all of this work very well for us is that gravity as an acceleration, we need that to be constant. And as Newton was doing all of his experimentations and measuring the acceleration due to gravity, what he came up with is that gravity was approximately 9.8 meters per second squared. And this is, for all arguments, a constant as long as we're on the surface of the Earth. The acceleration due to gravity will change if we go somewhere besides the surface of the Earth, but as long as we stick to the surface of the Earth, we can treat the acceleration as a constant. Now, the reason we need that to be a constant is because we are now going to jump into those calculus expressions that we had from the previous video, and we want to use these to produce some algebraic expressions that combine all of the terms that we have so far been using. We've had displacement, we've had velocity, which if we are in fact accelerating, that velocity will change. So we'll have initial and final velocity values. Technically, the displacement will contain the initial and final position values, but right now we're really just more interested in how far we move. And then all this stuff fits together with some relationship that is dependent on time. So what we have here are 5 variables. These are what we call our 5 kinematic variables, or 5 kinematic terms if you prefer. And what we want to do now is we want to produce some algebraic equations that involve these 5 variables. And we're going to produce more than one equation. In fact, we are going to produce 5 kinematic equations. So why 5? Well, why not? The more equations we have, the more information we have, the more that we can do with the physics. But as it turns out, these 5 kinematic equations that we're going to produce, each equation will only use 4 of the listed terms. So of all 5 equations, there will be one equation that leaves out displacement. Displacement will not show up anywhere inside that one equation. There will be another equation that does not utilize initial velocity. There will be one equation that does not use final. There will be one equation that doesn't use acceleration. And there will be one equation that does not use time. Now we are going to produce these 5 equations given what we know about calculus. So we're gonna go ahead and fast forward to present day with everything that we know about the calculus, and we're going to use these instantaneous rate expressions to produce the 5 kinematic equations that we're going to use to describe the motion of all the objects that we're going to be using in our class. So here we go. Number 1 rule for kinematics: the acceleration has to be constant. Well, we had 2 expressions up top that defined acceleration. We said that the acceleration could be defined in one of these 2 ways. And then we had that 3rd equation that defined the velocity. And we're going to go ahead and try our best to use all 3 of these just because we have them. And so let's take the easiest of them. Let's try the velocity equation. Now, acceleration has to be constant. Okay, well, the definition of acceleration is that you have a changing velocity. If you have a changing velocity, then this velocity term is not constant. That means that the ratio of the change between our position and our time is not constant. And when it comes to these calculus expressions, keep in mind this is still a ratio of 2 terms, and we can treat this algebraically by moving those terms around. I could very easily multiply both sides of this expression by dt. Algebraically, what you do to one side, you do to the other. And so we have v dt equals dx. And this is what we call our separation of variables. I have the changing x term on one side of the expression and the changing time term on the other expression. Now this does assume that our velocity is a time-dependent expression, and it is. But the next step would be to take this differential expression and turn it into an algebraic expression. So how do you take a derivative and turn it back into just a regular algebraic expression? Well, to do that, we would integrate. Integrating the right side is very straightforward. dx is going to integrate back to x. But I don't have a function that tells me what the velocity is doing with respect to time. I don't have any way of actually integrating the left-hand side, and so this approach is not going to help us, unfortunately. So I just wanted to get that out of the way. Also because there is nothing in this expression that we can use that guarantees that we have a constant acceleration, because there's no acceleration in this expression. So let's go over to the expressions that actually do have acceleration in them, and we are going to insist that we are working with a constant acceleration. And I'll go with the first expression here. And just like before, I want to perform a separation of variables. So I will take both sides of the expression and I will multiply it by dt. So this is what we call our separation of variables. I have a dt equals dv. And because the acceleration is a constant, technically the acceleration is not a function of time. So the acceleration does not depend on the time. I'm still going to attempt to integrate both sides with respect to the variables on each side. When I integrate the right-hand side, dv integrates back to v. But what happens when you integrate a constant? Well, similar to what was happening over here with our derivatives, if we integrate some expression with respect to x, a is a constant, that's just going to come along for the ride. And we end up, whoops, that is not right. We have 1 over n plus 1 as our expression. So whatever the constant is out front in our derivative process, it's just going to come along for the ride, and so the acceleration will come along for the ride. And our integral of dt, well, that's just going to integrate to t. But if we integrate using this method, this is what is known as an indefinite integral. If we do this, then we are going to have to add a constant of integration to one side of the expression. It doesn't matter which side, but there has to be a constant of integration included. Unless we turn this into a definite integral. And we can do that very easily if we, come on, eraser. There we go. We can do that very easily if we set some limits to our integral. Now, everything that we have in front of us is in general form. We have a generic acceleration, we have a time interval, a velocity interval. We have no idea where we're starting or stopping our measurements from. But that's actually okay, because we can set up our limits to be general limits as well. If we're going to be changing our velocity, well, let's go from whatever the initial measurement is to the final measurement. And if we're going to be changing our time, let's go from the initial time measurement to the final time measurement. Now when we take our integral, we actually have limits. And when we get our integration taken care of, we can evaluate at the limits. So v evaluated at final and initial is going to be v final minus v initial. Time evaluated at t final and t initial is t final minus t initial. But each of these are just delta statements. We have delta t and delta v with an a out in the front there. And if we just do a quick little rearrangement, we see that, oh, we've just reproduced the definition of acceleration. And like, this is something we already knew. And we just wasted 20 minutes reproducing something that we knew. But that is not a bad thing. It's always good if you can reproduce an outcome using a different approach and a different method. But here's something that you probably didn't think of. Keep in mind, delta t is too big, and so the best that we can hope for here is an average acceleration. Well, tell me this. What is the average of a constant? This whole time we've been saying we have to have a constant acceleration. So what's the average of a constant? It's just the constant. And so the average acceleration is equal to the constant acceleration that we used up above. Well, again, this isn't really that helpful. Is this the kinematic equation that we're supposed to be using? Because we said that there should be 4 terms in there. I'm only counting 3. We've got acceleration, time, and velocity. So let's backtrack a couple of steps in our math to right here. On the left side of the equality, I have a times the difference in the time interval, delta t, which equals the change in the velocity terms. And I'm going to go ahead and add the velocity term, v naught, to each side, because now that the calculus is over, our next job is to make our answer look like the book's answer. So we now have v naught plus a times delta t equals v final. And the last thing I'm going to do is I'm going to take that idea of delta t, which is t final minus t initial, and we'll just make life easy on ourselves, and we'll say that we're going to start our stopwatch at 0 seconds. And if that's the case, then the final time value is the time interval delta t, and the book is just going to take that time interval and call that generic t. So the time value that gets entered into this equation is going to be the value of the time interval, delta t. And now we have our first kinematic equation. Our first equation is that the final velocity is equal to the initial velocity plus the acceleration times time. So all I've done is I've switched the 2 sides of the equation there. Now we can go through and we can vet this equation by checking the units. Over here we have meters per second. Initial velocity is also in meters per second. We have meters per second squared for acceleration times time, which is also in seconds, which is going to cancel with one of the seconds down there. So all the terms are in meters per second, so that matches up. But let's see if this makes sense. Does this equation make sense? So let's go back to our car or our truck at the stoplight. So you're at the stoplight, the light turns green, you hit the accelerator, and you accelerate at a rate of 2 meters per second squared for 10 seconds. So what is your final velocity going to be at the end of that 10 seconds? That is the question. Well, you have an equation up top which requires 3 pieces of information so that you can solve for a 4th unknown. The unknown that we're trying to solve for is the final velocity, so I need to know what are those 3 pieces of information. Well, I know what the acceleration is, that was given, 2 meters per second squared. I know what the time is, 10. But the initial velocity wasn't given to me. Or was it? Technically, we're at a stoplight, so what should you be doing? You should be stopped. And when the light turns green, your vehicle is going to start with an initial velocity of 0. There's the final piece of information. And so we end up with a final velocity of 20 meters per second. The one variable that did not show up in this expression was the displacement. As this car is accelerating down the road, there will be a displacement associated with it, but that term did not show up in the equation itself. So what we're going to see as we're producing these equations, we have our first kinematic equation here. We are going to have missing terms from these equations. And the term that is missing from this first equation is the displacement. As we go through and we produce the other 5 equations, we will, as mentioned before, have each term missing from one of those subsequent equations. And so I call this our missing column, because it's a lot easier to pinpoint the one term that is missing as opposed to trying to count up the 4 required terms that you need to make the equation. Now please don't misunderstand. When I say missing, I don't mean that this is what we're trying to solve for. I mean that this term is completely absent from the mathematics. Well, so we've got 4 more equations that we have to make. I'm going to go ahead and end the video right now, because this is quite a bit to absorb for one video lecture. But we're going to continue our work with, oops, I didn't want to use the eraser there. We want to continue our work with these calculus rates and see if we can produce some more equations, preferably not equations that we already know. All we did there was we reproduced something we already knew. We want to see if we can make something we don't already know. And we've got 4 more chances to do just that. So I will see you at the next video.